Okay, so in the SN2 mechanism, which stands for substitution, that is nucleophilic and bimolecular, we're going to show that both reactants are involved in the rate determining step, and in fact there's only one step. So it's pretty confusing that SN2 only has one step. The key thing to remember about SN2 is that there are going to be two arrows in the same step, and that both reactants are going to be involved in the first step. So we've got one bromobutane and we've got hydroxide. I'm going to sort of simplify how I'm writing the one bromobutane. I'm going to put the Br here at the end, and then the rest of the molecule, so the other 3 carbons and 7 hydrogens, I'm going to condense down like that. You're welcome to do this also if it helps you save some space. So there's one of my reactants. And unlike SN1, where the halogen-alkane is the only reactant involved in the first and rate determining step, now I'm also going to draw hydroxide. Key things here is drawing at least one lone pair. I just assume draw all 3. And then I'm going to start drawing the curly arrows. So far I've done my 2 reactants. That's the first part that I need to remember with SN2. And the second part is the 2 curly arrows. So I'm going to draw an arrow from a lone pair, ideally, and show it going directly to the carbon atom. So curly arrows, full curly arrows are showing bond formation and bond breaking. So the lone pair from the nucleophile is getting donated to the carbon atom, which is slightly positive from this polar bond here. And that's going to cause this bond to break. This is an example of heterolytic fission, where both of the electrons are going to go to one atom, and we'll end up creating some ions. So that's my first step. You're probably receiving a mark for the first curly arrow being correct from the lone pair to the carbon, and for the second curly arrow coming from the bond and going to the Br atom. Moving on to the next step. It's actually not a next step, sorry. But in SN2, what they want you to show is what we call a transition state. So we're going to show what is believed to exist at the point in time when the bonds are both in the process of breaking and forming. It looks a little bit like SN1. This is what SN1 would look like, where you would have a carbocation here. But in SN2, we're going to show something slightly different, which is that we're going to show the Br breaking off, and we're going to show the hydroxide attaching. Now, since everything is combined here, the overall charge is negative. My overall charge in my reactants was negative. I had a hydroxide with a negative charge. So this is my transition state. And the transition state has an overall negative charge, and it shows the bonds breaking and forming. Notice I flipped around the hydroxide so that the O is shown forming a bond to the carbon. And I've got these dotted lines that represent bond breaking and forming. So this correct transition state is a mark. You don't need to call it transition state, but you do need to put it in brackets. You do need to imply the negative charge, and you need to show those bonds breaking and forming. After this, we just show the reaction complete. So this is all taking place in one step technically. So on a potential energy diagram, it's just a one-step reaction. It doesn't get 2 energy hills. There's just one step to take place. When we're done, we're going to have that Br minus now. So the bromine has been kicked off as a bromide ion. It's called the leaving group. And now I've got butane 1-ol instead of 1 bromobutane. So I could draw this in different ways, but if we want to be consistent, I could draw my H7C3, then my CH2, and then the OH. So the OH has substituted for the bromine, and now I've shown it in a clear SN2 fashion, 2 curly arrows in the same rate determining step to distinguish it from SN1.